A team of physicists spent years trying to do something that sounds almost boring compared to the usual quantum computing headlines. They were not trying to build a faster chip or break a new speed record. They were simply trying to confirm that some of the field's most celebrated breakthroughs were actually real. What they found instead was genuinely unsettling, not because they uncovered fraud or deception, but because they discovered that some of the most exciting signals ever published in this specific corner of physics, results that made international headlines and shaped years of subsequent research funding, could be explained by considerably simpler, considerably less exotic physics than anyone had originally claimed. And then, in a twist that turned out to be almost as important as the scientific finding itself, these same researchers spent more than 2 full years struggling just to get their findings published at all, repeatedly turned away by the very same prestigious journals that had happily published the original, more exciting claims in the first place. This is a story about a quantum computing breakthrough that may not have been what it seemed, but it is also, in a genuinely important way, a story about something broken inside the machinery of science itself. And today, we are going to walk through both halves of that story together. To understand why this particular replication effort matters so much, you first need to understand exactly what topological quantum computing promises, and why researchers have spent nearly 2 decades chasing it with such genuine intensity. We touched on this specific technology in detail in a previous video on this channel covering Microsoft's own Topological quantum computing program, but it is worth revisiting the core concept here because it sits at the center of this entire story as well. Most quantum computers being built today, including the superconducting processors, companies like Google and IBM have built their reputations around store fragile quantum information in a single, localized physical location, making that information genuinely vulnerable to any tiny disturbance nearby. Topological quantum computing offers a fundamentally different, theoretically far more robust approach, splitting quantum information across 2 physically separated locations using an exotic quasi-particle called a Majorana. Zero mode, meaning a disturbance hitting one location literally cannot corrupt the information stored across the pair as a whole. If that theoretical protection genuinely holds up in practice, it would represent one of the most significant breakthroughs in the entire history of quantum computing, potentially requiring dramatically less external error correction than every other current approach. That enormous potential payoff is exactly why this specific research area has attracted so much attention, so much funding, and, as this particular story reveals, so much pressure to report exciting, headline-grabbing results. The team behind this specific replication effort was led by Sergei Frolov, a physics professor at the University of Pittsburgh, working alongside collaborators from the University of Minnesota and a research institute in Grenoble, France. Frolov is not a new or unfamiliar name in this particular corner of physics, and understanding his specific history here matters for appreciating exactly why this new work carries so much weight. Back in 2021, Frolov was directly involved in the specific process that led to the retraction of a high-profile Nature paper, one originally published by a Microsoft-backed research team based in Delft, the Netherlands, after Outside. Researchers, Frolov very much included, demonstrated that the underlying data could actually be explained by ordinary material imperfections, rather than the genuine topological particle the original paper had claimed to discover. That earlier episode established Frolov as one of the field's most credible, most technically rigorous skeptics. Someone with a genuine demonstrated track record of catching exactly this kind of overstated claim through careful, patient reanalysis, rather than simply expressing vague, unsupported doubt. This new project represented Frolov's team taking that same careful, skeptical approach and systematically applying it across multiple additional claimed breakthroughs in this same research area, rather than examining just one isolated paper in isolation. Here is what the team actually found when they carried out this systematic replication effort. Across multiple separate experiments, each one originally published as a genuine, exciting step forward for topological quantum computing in leading scientific journals, Frolov's team consistently identified alternative, considerably simpler explanations for the exact same underlying data. In case after case, the specific experimental signals that earlier research teams had presented as strong evidence for genuine topological physics turned out to be equally, sometimes even better, explained by more mundane, considerably less exotic physical effects. Things like ordinary disorder within the experimental wire or accidental pockets of trapped electrical charge called quantum dots, precisely the same category of mundane, non-topological explanation that had already sunk that original 2021 Delft paper years earlier. This is not a story about any single isolated mistake. It is a story about a recurring, systematic pattern across an entire subfield of physics, where genuinely ambiguous experimental signals kept getting interpreted again and again in the most exciting, most headline-friendly possible direction. rather than being weighed evenly against the more mundane, more probable alternative explanations sitting right alongside them. It is worth pausing here to genuinely understand why this particular pattern kept repeating itself, because it is not simply a story about researchers being careless or dishonest. The underlying physics, genuinely, is difficult, and the specific experimental signatures researchers are hunting for when searching for genuine topological states are, by their very nature, extremely faint and extremely easy to confuse with other, more common physical phenomena occurring inside the exact same devices. When you are running a genuinely difficult experiment, searching for a specific, theoretically predicted signal, and you finally see something that looks like what theory predicted, there is an enormously powerful, entirely human pull toward interpreting that signal as confirmation of what you were hoping to find, rather than continuing to rigorously test whether some more boring, more probable alternative explanation might actually be responsible instead. That specific psychological and institutional pressure, not necessarily deliberate deception, but a genuine, well-documented, team spent years systematically documenting across multiple separate research groups and multiple separate published papers. If you find this kind of honest, careful examination of how scientific claims actually get tested and sometimes overturned genuinely valuable, go ahead and hit that like button right now. It really does help this channel reach more people who want the complete, technically grounded picture rather than just the more exciting, less scrutinized version of these stories that tends to circulate more widely. And if you want to keep tracking exactly how this ongoing scientific reckoning within quantum computing continues to unfold, subscribe, because based on everything we are about to walk through, this particular story is genuinely still developing. Now let's talk about the second half of this story, the part that arguably matters even more than the specific physics findings themselves, because it reveals something genuinely troubling about how the broader scientific publishing system currently handles exactly this kind of important, difficult replication work. Frolov's team did not simply run their experiments, write up their findings, and get them published in a reasonable, timely fashion, the way you might expect genuinely important scientific work to move through the system. Instead, according to the team's own account, their individual replication studies repeatedly struggled to gain acceptance from the same prestigious scientific journals that had originally published the more exciting, less scrutinized claims these studies were specifically designed to test. Editors reportedly rejected these replication papers on the grounds that the work supposedly lacked sufficient novelty, or on the grounds that the broader field had already moved on from these specific claims after a few years had passed, treating genuinely important, unresolved scientific questions as though they had some kind of expiration date attached to them, well before those questions had actually been properly, rigorously settled through careful, independent verification. That specific institutional bias, treating original, exciting claims as inherently more publishable than the careful replication work needed to actually verify whether those claims hold up under scrutiny, reflects a genuinely significant, well-documented structural problem running throughout much of modern science, one that extends considerably beyond this one specific corner of quantum physics. Scientific journals, understandably eager to publish genuinely novel, headline-worthy findings that will attract citations, media coverage, and prestige for both the researchers and the publication itself, have historically undervalued the slower, less flashy, but genuinely essential work of independently verifying whether earlier claims actually hold up once other researchers attempt to reproduce them using their own equipment and their own careful analysis. This specific bias creates a genuinely troubling asymmetry, where it is often considerably easier to get an exciting, if ultimately incorrect, breakthrough claim published quickly than it is to get the careful, rigorous replication work that might eventually correct that same claim published at all, a genuinely dangerous imbalance for any field of science that depends on accurate, reliable knowledge accumulating over time. Frolov's team responded to this specific institutional obstacle in a genuinely clever, strategically important way, one worth understanding in detail because it offers a real practical lesson for how this kind of important replication work might eventually break through similar institutional resistance in the future. Rather than continuing to submit each individual replication study separately, facing repeated rejection one paper at a time, the team specifically combined several distinct replication efforts together into a single, considerably more comprehensive paper, one built around a broader, more ambitious argument, extending well beyond simply debunking any one individual claim. That broader paper made two genuinely important points simultaneously. First, it demonstrated, across multiple separate experiments, that even genuinely striking experimental signals, the kind of results that had previously been celebrated as major breakthroughs, could sometimes be explained through entirely different physics once more complete data was actually examined carefully. And second, it specifically proposed concrete reforms to how this kind of research gets conducted and reviewed going forward, calling explicitly for greater data sharing between research teams and considerably more open, honest discussion of alternative interpretations before any given experimental result gets celebrated publicly as a confirmed, settled breakthrough. Even with that more strategically framed, more ambitious combined paper in hand, the path to actual publication remained genuinely difficult. And the specific timeline involved is worth sitting with for a moment because it illustrates just how much resistance this kind of important corrective work can face even when it is eventually, ultimately successful. The paper was originally submitted for publication all the way back in September of 2023, and it underwent what researchers involved in this specific process have since described as a record 2 full years of peer and editorial review before finally being accepted and published in the journal Science on January 8th of this year. 2 years. For a paper specifically designed to correct the scientific record on claims that had already been publicly celebrated. Publicly funded and publicly cited for years, the broader scientific community needed a genuinely extensive, genuinely prolonged period of discussion and debate before the field, as a whole, proved willing to seriously entertain the possibility that some of its most exciting, most widely celebrated earlier results might actually be incomplete or mistaken. It is worth connecting this specific story directly back to the Microsoft topological quantum computing dispute we covered in considerable detail in a previous video on this channel, because understanding the connection between these two stories genuinely deepens your appreciation for exactly how significant this broader pattern actually is. The critique, published by Henry's, Leg in Nature this past June, specifically challenging Microsoft's own Majorana 1 chip claims, did not emerge in some kind of scientific vacuum, disconnected from this broader replication crisis. It arrived directly on the heels of, and was published in the exact same general period as, this considerably broader, more systematic body of replication work that Frolov's team had spent years struggling to bring into public view. Microsoft's own history includes that same 2021 retraction we mentioned earlier, involving that same Delft research team, and Frolov himself was directly, personally involved in identifying the specific problems with that original claim. Seeing these two stories together, rather than in isolation, reveals something genuinely important about the broader state of topological quantum computing research as an entire field, not simply about any single company's specific claims. This is a research area with a well-documented, repeatedly demonstrated pattern of exciting, headline-grabbing signals turning out to have simpler, less exotic explanations once independent researchers apply sufficiently careful, sufficiently patient scrutiny, a pattern that predates Microsoft's own specific claims by years and that appears to extend well beyond any single company or any single research team. There is a genuinely important, broader lesson here about how the public, including everyone watching this video right now, should actually consume and interpret quantum computing headlines going forward, one that extends considerably beyond this one specific research area. When a genuinely exciting scientific claim gets published, especially one involving a technology as commercially and strategically significant as quantum computing currently is, the initial wave of media coverage almost always arrives considerably faster and considerably more prominently than any subsequent, more careful scientific scrutiny that might eventually challenge or meaningfully qualify that original claim. Frolov's team's paper took more than 2 years just to get published, meaning the original, more exciting claims their work eventually challenged had already enjoyed years of essentially uncontested media coverage, research funding, and broader scientific influence before this more careful, more skeptical counter-analysis finally made it into print. That specific asymmetry, exciting claims traveling fast, careful corrections traveling considerably slower, is exactly why maintaining a healthy, informed skepticism toward any single, individual quantum computing announcement, however impressive and however well covered in the mainstream press, remains such a genuinely important habit for anyone trying to actually understand where this field truly stands, rather than simply where its most recent, most exciting headline happens to claim it stands at any given moment. It is also worth being fair and genuinely balanced about what this specific story does and does not actually prove, because responsible coverage requires exactly this kind of careful, measured framing, rather than simply swinging from uncritical enthusiasm toward uncritical cynicism. Frolov's findings do not prove that topological quantum computing is fundamentally impossible, or that every single claim ever made in this specific research area has been mistaken or overstated. Genuine, careful, well-validated progress continues happening across this entire broader field, including work from Frolov's own research group, which continues actively investigating these same underlying physical systems using considerably more rigorous, considerably more skeptical methodology than some of the earlier work his team specifically challenged. What this story actually demonstrates is something more specific and, in its own way, more genuinely useful, that the broader scientific and media ecosystem surrounding quantum computing has a well-documented structural tendency to celebrate exciting claims, considerably faster than it manages to properly scrutinize them, and that researchers doing the genuinely essential work of careful patient verification often face real, meaningful institutional obstacles, simply trying to get their corrective findings into print at all. There is also a genuinely important, forward-looking dimension to this story worth exploring, because Frolov's team did not simply document this specific problem. They proposed concrete, practical reforms, specifically designed to help prevent this same pattern from continuing to repeat itself going forward. Their call for greater data sharing between research teams addresses a genuinely specific, genuinely important technical gap we actually discussed in our previous video covering the Microsoft dispute, where Henry Legg's own critique depended heavily on pulling raw, underlying measurement data directly from a public repository, since Microsoft's original paper had published only finished, processed classification results rather than the complete raw data itself. Frolov's broader push for considerably more open data sharing across this entire research area reflects exactly the hold more broadly across this entire research community going forward, requiring considerably more routine, considerably more comprehensive data sharing as a standard practice rather than an unusual exception. It could meaningfully reduce exactly the kind of prolonged multi-year uncertainty this whole story has walked through, allowing genuine scientific disputes to get resolved through direct, independent examination of complete data considerably faster than the years-long process Legg, Frolov, and numerous other researchers in this specific field have all had to individually endure. It is also worth considering what this entire story reveals about the sheer institutional pressure driving so much of the recent excitement surrounding quantum computing more broadly, a pressure we have discussed from several different angles across this entire series of videos on this channel. Companies like Microsoft face enormous competitive and financial pressure to demonstrate visible, headline-grabbing progress toward their own ambitious quantum computing timelines, pressure that comes directly from investors, from government funding agencies, and from the broader competitive landscape involving rivals like Google and IBM, all of whom we have discussed extensively across previous videos covering their own respective quantum computing strategies. That same broader pressure extends into academic research as well, where individual researchers and entire research groups depend heavily on publishing genuinely exciting, headline-worthy results in order to secure continued funding, continued career advancement, and continued institutional prestige within an increasingly competitive, increasingly high-stakes research environment. Frolov's own work suggests that this pervasive pressure toward exciting, headline-friendly results may have contributed, whether consciously or not, to a genuine, systematic pattern of ambiguous experimental signals repeatedly getting interpreted in the most exciting available direction, rather than being weighed evenly and skeptically against the more mundane, ultimately more probable, alternative explanations, sitting right alongside them the entire time. It is worth spending a bit more time understanding exactly why quantum dots, the specific alternative explanation Frolov's team kept finding underneath these earlier, more exciting claims, are so genuinely difficult to distinguish from real topological signatures in the first place, because that specific technical difficulty explains a great deal about why this particular research area has proven so genuinely prone to exactly this kind of repeated, well-intentioned misinterpretation. A quantum dot is essentially a tiny accidental pocket where electrical charge becomes trapped within a nanoscale device, something that can form unintentionally due to minor imperfections in how the underlying semiconductor material was manufactured, entirely separate from any deliberate engineered topological physics the researchers were actually trying to create and study. Under certain specific measurement conditions, these accidentally trapped charge pockets can produce electrical signals that look remarkably, sometimes almost indistinguishably, similar to the genuine signatures researchers are specifically searching for when hunting for real Majorana zero modes, particularly when researchers are only examining a limited slice of the available data rather than the complete, comprehensive data set a device is actually capable of producing. This is not some obscure, rarely encountered technical footnote. It represents one of the single most persistent, most well-documented sources of confusion running throughout this entire two-decade research effort, precisely the same. Underlying alternative explanation that sank the original 2021 Delft paper and precisely the same alternative explanation Henry Legg specifically raised in his own more recent critique of Microsoft's Majorana 1 claims that we discussed in detail in our previous video on this channel. There is also a genuinely important, more technical dimension to Frolov's specific critique worth understanding, because it goes beyond simply identifying alternative explanations for individual, isolated experimental results. Frolov's team specifically emphasized that many of the original papers they examined had presented what researchers in this field sometimes call smoking gun evidence, meaning a single, particularly striking experimental signal presented as compelling, near-definitive proof of a genuine topological state, without adequately demonstrating that same signal alongside a comprehensive, systematic exploration of the device's full parameter space. That specific pattern, highlighting one particularly clean, particularly exciting-looking measurement while providing considerably less attention to the broader, messier context surrounding that single measurement, is exactly the kind of selective presentation that Henry Legg's more recent critique of Microsoft's own topological gap protocol software specifically identified as well, where an automated tool reportedly displayed only the single most promising region of a given device, while effectively hiding the messier, less conclusive readings found everywhere else across that exact same physical chip. Seeing this same specific pattern, emphasizing a single striking result while providing considerably less scrutiny to the broader surrounding data, appear independently across multiple different research groups, multiple different specific devices, and multiple different published papers spanning several years, suggests this represents a genuine systemic pattern within this particular research community, rather than any single isolated incident specific to one particular team or one particular company. It is also worth considering the specific human and institutional dynamics that made this particular pattern so difficult to correct for so many years, because understanding those dynamics offers genuinely useful insight into how science, as an actual human institution, rather than an idealized, purely rational process, sometimes struggles to correct itself even when the underlying evidence for doing so genuinely exists. Researchers working in this specific, highly competitive corner of physics operate within research groups that depend heavily on continued funding, continued publication in prestigious journals, and continued positive media attention in order to sustain their careers and their laboratories over the long term. Reporting a genuinely ambiguous, inconclusive result, one that might ultimately turn out to be explained by mundane quantum dot physics rather than genuine topological phenomena, offers considerably less career and funding benefit than reporting a clean, exciting, headline-worthy breakthrough, even when the underlying complete data might actually support both interpretations roughly equally well. This is not necessarily a story about individual researchers deliberately, knowingly overstating their results. It is, more accurately, a story about a broader research and publishing ecosystem that systematically rewards exciting, confident claims considerably more generously than it rewards the genuinely difficult, genuinely valuable work of maintaining rigorous, patient skepticism, particularly when the underlying experimental signals themselves are genuinely, legitimately ambiguous and open to multiple, reasonable interpretations. It is also worth placing this specific story within a considerably broader pattern that has played out across multiple different scientific fields over the past decade or so, a pattern often referred to more generally as the replication crisis, a term that gained widespread attention initially within psychology and certain areas of biomedical research before gradually being recognized as a genuine structural challenge extending across essentially every field of modern science, physics very much included. The core underlying problem remains remarkably consistent across all of these different fields. Scientific journals and the broader academic incentive structure surrounding them have historically rewarded novel, exciting, positive findings considerably more generously than they reward the careful, patient work of replicating and verifying those same findings, creating a systematic bias, where exciting claims accumulate and spread considerably faster than the corrective replication work needed to properly test whether those claims actually hold up under sustained scrutiny. Frolov's own experience, waiting more than 2 years and facing repeated rejection before finally getting his own careful counter-evidence published, represents a genuinely clear, documented example of exactly the same broader replication crisis playing out within the specific context of topological quantum computing research, suggesting that this particular subfield of physics is not somehow uniquely flawed or uniquely prone to overstated claims, but rather represents one more specific, well-documented instance of a considerably more widespread, considerably more systemic challenge running throughout modern scientific publishing more broadly. There is also a genuinely encouraging dimension to this story worth highlighting, because despite the genuine institutional resistance Frolov's team faced, their work ultimately did succeed in reaching publication, And it succeeded specifically in one of the most prestigious, most widely read scientific journals in the entire world. That eventual success, however delayed and however difficult to achieve, demonstrates that the broader scientific self-correction process we have discussed across several previous videos on this channel, the same adversarial, evidence-based process that led to genuine resolutions in the ongoing Google versus IBM quantum supremacy disputes, and the same process currently playing out around Microsoft's own contested Majorana claims, does ultimately function, even when it moves considerably slower and faces considerably more institutional friction than anyone might reasonably hope for. Science, as an overall system, remains genuinely self-correcting over sufficiently long time horizons, even when individual claims sometimes enjoy years of largely uncontested acceptance before more careful, more patient scrutiny finally catches up with them. The genuinely important lesson here is not that this self-correction process is broken beyond repair, but rather that it currently operates considerably slower and faces considerably more resistance than most people outside this specific field probably assume. A genuinely important piece of context for understanding exactly how much confidence to place in any single individual quantum computing announcement at the specific moment it first gets published. Before that same careful, patient verification process has actually had sufficient time to run its full course. It is also worth noting that Frolov's own research group has continued actively working in exactly this same research area, rather than simply abandoning the entire field of topological quantum computing after uncovering these specific problems with earlier claims. That detail matters because it demonstrates that this entire replication effort was never actually motivated by a desire to discredit or dismiss the underlying scientific goal of building genuinely working topological qubits, but rather by a genuine, constructive desire to ensure the field's foundational claims actually rest on sufficiently solid, sufficiently well-verified evidence before the broader research community, along with the massive financial investments increasingly flowing into this specific technology from companies like Microsoft, continues building an increasingly ambitious research and commercial agenda on top of that same underlying foundation. Frolov's specific push for greater data sharing and more open discussion of alternative interpretations represents a genuinely constructive, forward-looking response to the problems his team identified, aimed at making the entire field considerably more resilient and considerably more scientifically rigorous going forward, rather than simply cataloging past mistakes for their own sake. So where does this actually leave the broader field of topological quantum computing? And more importantly, where does it leave you? As someone trying to genuinely understand and follow this rapidly evolving technology going forward? The honest, complete answer requires holding several distinct truths together simultaneously, rather than collapsing this genuinely nuanced story down into either uncritical excitement or uncritical dismissal. Topological quantum computing remains a genuinely promising, genuinely important area of ongoing research, one that continues attracting serious, talented researchers and serious, substantial funding precisely because its theoretical potential remains so significant if the underlying physics can ultimately be made to work reliably. But this specific field also carries a genuinely well-documented, repeatedly demonstrated history of exciting claims subsequently proving to be less definitive than their original headlines suggested, a pattern that predates Microsoft's own recent, still actively disputed claims, and one that Frolov's team has now formally, rigorously documented across multiple separate research groups and multiple separate published papers after years of institutional resistance, specifically trying to keep that same important corrective work out of print. The genuinely important lesson to take away from this entire story, one that applies well beyond this single specific research area, is that the pace at which exciting scientific claims travel through headlines and media coverage almost never matches the pace at which those same claims actually get properly, rigorously verified by careful, independent researchers working through the genuinely slow, genuinely difficult process of replication and scrutiny. The next time you encounter a dramatic new quantum computing headline, whether it involves topological qubits, superconducting processors, or any of the other approaches we have covered extensively across this entire series of videos, it is worth remembering Sergei Frolov's own 2-year struggle just to get his own careful, rigorous counter evidence into print, and asking yourself a genuinely useful question before accepting any single headline claim at face value. Has this specific result actually survived the kind of patient, skeptical, independent scrutiny that separates a genuine, lasting scientific breakthrough from an exciting signal that simply has not yet met its own Sergei Frolov? Someone patient and rigorous enough to check whether the more exciting explanation was actually the correct one all along. There is one final, genuinely important point worth leaving you with, something that ties this entire story back to a broader theme running throughout this whole series of videos exploring the rapidly evolving world of quantum computing. Every single story we have covered together, Google's Willow processor and its genuinely celebrated error correction milestone, China's rapid progress across multiple different quantum hardware approaches, IBM's massive manufacturing, investments, and now this genuinely important reminder about how carefully even the most exciting claims deserve to be scrutinized before being fully accepted, ultimately points toward the same underlying conclusion. This is a genuinely young, genuinely difficult, genuinely still maturing field of science, one where extraordinary claims continue arriving at a remarkable pace, and where the healthy, adversarial process of testing those claims, sometimes confirming them, sometimes meaningfully narrowing them, and sometimes, as we just walked through in considerable detail, revealing that the more exciting explanation was not actually the correct one at all, remains just as essential to the field's genuine progress as the original breakthrough claims themselves. Frolov's story is, in its own way, just as important a part of quantum computing's ongoing development as any single dramatic new chip announcement, precisely because it represents the genuinely difficult, genuinely unglamorous work of making sure the field's foundational claims can actually bear the weight of the billions of dollars, the years of research funding, and the enormous public attention increasingly being placed on top of them. Science does not always move quickly, and it does not always move fairly, but stories like this one demonstrate that, given enough time and given researchers patient and stubborn enough to keep pushing even after repeated rejection, it does still tend to move in the right direction eventually, even when that direction turns out to be considerably less exciting than the original headline promised. That, ultimately, might be the single most useful takeaway from everything we have walked through together today. A field this young, this well-funded, and this genuinely important will keep producing dramatic headlines for years to come. And most of those headlines will arrive long before the kind of careful, patient scrutiny this video has focused on has had any real chance to catch up. That gap between announcement and verification is not a flaw unique to quantum computing specifically. It is simply the honest, sometimes uncomfortable pace at which real science actually moves, and understanding that pace, rather than expecting every headline to already represent a fully settled, fully verified fact, is exactly the kind of informed patience this entire channel has tried to model across every single story in this series, this one very much included.